Good morning and welcome to some more discrete math. We're in chapter 10 and this video is going to talk about multiplying matrices. If you already know how to multiply matrices, it is not necessary to watch this video. But if you've never multiplied matrices before, then hopefully this video is going to help you through it. It's not a difficult concept. So here we go, matrix multiplication. So the first thing we have to do is we have to talk about what are these things, matrices, okay? So I want to suppose that we have a matrix A. I just give it a name. And I'm going to make it up, right, while I'm doing this. And maybe it's got a 3 and a 7, 6, 2, 1.5, and minus 4.3. And it looks like that. Okay, and we notice a couple of things about this matrix. We note that it has 3 rows. And we note that there are 2 columns. So we say that A is a 3 by 2 matrix. Okay, so the first number here always indicates rows. The second one indicates columns. And sometimes we'll talk about matrices. We'll get a little bit more theoretical here rather than actually having numbers in here. We might say A is equal to, and we might write something like this. We might write little a11, a12, a21, a22, a31, a32, where at least in this example here, it's understood that a11 is equal to 3, and a12 is equal to 7, a21 is equal to 6, a22 is equal to 2, whoops, this is a mistake here. I need to be careful. I erase. A32 is equal to minus 4.3. Okay, so it's understood that any of these little lowercase a's can refer to any kind of real number that we're dealing with. And again, let me clean this up. My apologies about that. Okay. And again, when we use this kind of subscript there, if I'm using a lowercase and I say A sub I j, that's referring to the ith row and the jth column. Okay, so let's move this over a little bit and bring on another screen here. And what I want to do here is I want to think about this row, this matrix A here, in a slightly different way. What I'm going to do here is I'm going to talk about row 1, and I'm going to put a little arrow over it like that, and I'll explain that arrow later. Okay, but I'm going to go, this is equal to 3, 7. And I'm going to come over here and I'm going to say that R2, again, with an arrow over it, that's equal to 6 and 2. And I'm going to come over here and I'm going to say that R3, with a little arrow over it, is equal to 1.5 and minus 4.3. And again, notice I'm using, these are ordered pairs here. The order does matter. Okay, so another way that I could write A is I could say that A is equal to a matrix that looks like this. R1, R2, R3. Okay? And another way that I could do it is nobody says I just have to look at rows. I could also come over here and look at the columns. Okay, so here's a column, and notice that there are two of them. And I could say here that column 1 is equal to, and I just start going down. And I go, well, that's 3, 6, 1.5. And I could say that C2, and again, that arrow up there is important. We'll explain that in a little bit. And that would be 7, 2, and minus 4.3. 7, 2, minus 4.3. And now, not only can I write A this way in terms of these rows, but I could also come over here and write it this way in terms of the columns. Okay? Is that clear? If people don't like writing it this way, you could think of it this way if you want to. You could come over here and say this is really this 3, 6, 1.5, and this is equal to 7, 2, minus 4.3. And maybe you'd like to think of these columns here with the arrows over them as actual columns. These rows are rows, these columns are columns. When you think about these being represented this way, then I think it's easier to conceptualize this matrix looking this way. But recognize that both of these are the same. Okay, these are specifying the same matrices in terms of either rows or columns. Now, when I take something like this, let's just come over here and look at this R1. When I go R sub 1 and I put this arrow over it, and I say that this is equal to 3 comma 7. Okay, what the arrow means, that means that this thing is, in mathematics, we call that a vector. And there's a whole theory of mathematics called vector mathematics, linear algebra. Maybe you've heard all of these terms, and we're not going to spend a whole lot of time on this, but just realize when I put the arrow over here, it's a vector, and one of the properties of a vector is a vector is an ordered set. Okay, so meaning that we specify it with these brackets here, which means that the order matters. In other words, 3, 7 is not the same thing as saying 7 comma 3, which of course these would be equal if I were talking about sets and using the curly braces. Okay. The other thing is when we have a vector, sometimes we will talk about the dimension of a vector. And the dimension is just how many elements there are in the ordered set that we have here. So I would say here that the dimension of R1, this vector, this is equal to 2. And in fact, the dimension of R2 is equal to 2, and the dimension of R3 is equal to 2. Now, if I were to come over here and look at these column vectors over here, the dimension, for example, of C1 is equal to 3. In other words, there are 3 numbers here that make it up. So there is the notion of dimension. I'll just write the word here in case you don't understand my accent. Dimension. Okay, we talk about the dimensions of vectors. Okay, we need to talk about one other operation before we go ahead and actually start multiplying matrices, and we're doing this to try and make the calculations a little bit easier. So I want to go back to this discussion that we had about vectors, and I want to suppose I have an arbitrary vector. So here's a vector over here. I'm going to call it V1. I'm going to put an arrow over it, and I'm going to say that that's equal, and I'm just going to make some numbers up here. It's not important. 3, 5, and -1. And I'm going to come over here, and I'm going to create another vector, V2. And why don't we say that that's equal to 4, -6, and 2. Now, the one thing I want you to notice over here is that the dimensions of these, the dimension of V1 is equal to the dimension of V2. And in this case, it's equal to, well, there are 3 numbers in either one of them. There's 3. So it turns out that there is something called the dot product. It's sometimes also referred to as the scalar product. Of 2 vectors. And this is only defined if the 2 vectors have the same dimension. Okay, so it's defined here. And the way that we write this is we say V1, and we just put a dot there, and then we say V2. And what this is equal to is I take these first 2 numbers in the vector, in the 2 vectors, and I multiply them together. And then I go plus, and then I multiply the second 2 numbers together. So that would be 5 and -6. And to that I add the multiplication of the third numbers here. So it would be a -1 times 2. And this is equal to 3 times 4 is 12. And let's see, 5 times -6, that's going to be -30. And then I come over here and I go plus -1 times 2, that's -2. So let's see, that's -32 plus 12, that is equal to -20. So V1 dot V2 is equal to -20. Now, there are lots of interpretations of what this number means. For the purposes of multiplying matrices, we really don't care what it means, but this is going to help us calculate the product of 2 matrices. But what I'd like to do here is I would like to just give you a little bit of a notational indication here of things. Suppose I have a vector A, and that's equal to some A1, comma, A2, comma, A3, comma, all the way up to some A sub n. So this is an n-dimensional vector. And suppose I have a vector B, which is also an n-dimensional vector, B1, comma, B2, comma, B3, all the way up to B sub n. Then we would have that A dot B, like that, is equal to, and here's the notation here, the summation, okay, of I goes from 1 to n of A sub I times B sub I, okay? And some people would say that this is the actual definition right over here for the generalized dot product. All right, we are finally in a situation now to multiply two matrices, okay? Um, and here's the first unusual result about multiplying two matrices. Given matrix A, I'm going to say given matrices A and B, it is not always the case you can multiply them. Okay, that's a very, very important thing. So let's talk about when can you multiply matrices. If I want to multiply matrices, and I'll write that just like this, I'll just say AB. Okay, this would be the multiplication. It turns out we have to consider the dimensions of the matrices, of the individual ones. And there's got to be a very important property that is true. If A is, say, M by N, then it turns out that B has to be N by K. In other words, to be able to multiply two matrices together like this, it must be the case that these numbers right over here match each other. And that tells you something a little bit weird already. So for example, why don't I let A equal 2, 3, 1, 4, 6, 2. Okay, so we recognize that as 1, 2, 3 by 1, 2. This is 3 by 2. Then I'm going to have to B. Why don't I let B be something like this? 1, 2, 3, 4. 4, 1, 6, 3. Well, B is a 2 by 4. And I see that these match. So yes, I am able to multiply these two together. And in fact, here's the interesting thing. The result will be 3 by 4. It's almost like these guys in the middle cancel each other out. But this also shows you something else that's kind of interesting. In this situation here, notice I can multiply A times B, but notice I can't multiply B times A. If I tried to multiply B times A, I would have a 2 by 4 that I'm trying to multiply by a 3 by 2, and these middle numbers here don't match each other. Okay? So it turns out a very interesting property of matrix multiplication is that it is not always the case that if you can multiply A times B, that you could multiply B times A. The other thing that's interesting, and we really won't delve into this very far, it turns out that if you could do A times B and B times A, and of course I think you can see that's the case if they're square matrices. In other words, suppose A was 3 by 3 and B was 3 by 3, then clearly I could go A times B or I could go B times A, and the result will be a 3 by 3 matrix. It's not always the same matrix. So matrix multiplication in general is not commutative, but we're not going to be worried about that in this class. I just mentioned this for completeness. So let's continue now with how we would actually multiply these two matrices. And I'll show you two ways, and one way is based on the dot product that we talked about before. Okay, so basically you can see over here that I've got these row vectors here. I can think of A is really made up of these row vectors, and I'm going to just call them R1, and then I'm going to say there is R2, and there's R3, and again I will indicate them with these arrows over them. Okay, row, 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 and we can see that B is actually made up of these 4 column vectors. Column 1, column 2, column 3, and column 4. Okay, and we know that what I'm going to be getting here is I'm going to be getting a 3 by 4. Well, it turns out that AB, remember this is going to be a 3 by 4, okay, is equal to, and I'm going to come over here, and I'm going to draw this. And what's going to happen is it's going to be R1 dot C1, and then it's going to be R1 dot C2, and it's going to be R1 dot C3, and then it's going to be R1 dot C4, and I apologize, it's getting a little messy here. And then I think you can see the rest of the pattern. This is going to be R2 C1, this is going to be R3 C1, and you can see that this is going to continue all the way over here, and this is going to continue all the way over here to R3 C4. Okay, so the thing to think about is when you multiply the 2 matrices together, first just think about the size of the resultant matrix. And then the other thing to think about is okay, express the first one in terms of rows and the second one in terms of columns, and you basically just have to do all of those dot products. Now, this is one way to think about it. Another way to think about it is this way, and I'm going to just go AB is equal to, and I'm going to come over here, and I'm going to do it, and what happens is the number that goes over here is, I am just going to multiply 2, 3 times 1, 4. Notice I'm going the first row times the first column. Well, 2 times 1 is 2, and 3 times 4 is 12, and 2 plus 12 is 14. And now the one that goes over here, okay, again, that's going to be R1C2. So I'm going to go 2 times 3, or I'm going to go the vector 2, 3 times the vector 2, 1. Well, 2 times 2 is 4, and 3 times 1 is 3, and 3 plus 4 is 7. And then I'm going to come over here, and I'm going to go 2, 3, 3, 6. Well, 2 times 3 is 6. And 3 times 6 is 18, and 6 plus 18 is 24. And now I'm going to go 2, 3, and 4, 3. 2 times 4 is 8, and 3 times 3 is 9, and 8 plus 9 is 17. I'm going to stop circling them. So that's the first row. Now I've got to go to the second row. So I'm going to be multiplying these, or I'm going to be taking the dot product of these with this, 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 and this. So 1, 4, and 1, 4, well, that's going to give me 1 times 1 is 1, and 4 plus 4 is 16. 16 plus 1 is 17. And now I'm going to go 1, 4 dotted with 2, 1. 1 times 2 is 2, and 4 times 1 is 4. 2 plus 4 is 6. Now I'm going to go 1, 4 dotted with 3, 6. 3 times 1 is 3, plus 4 times 6, that's 24. 24 plus 3 is 27. And 1, 4, and 4, 3. 1 times 4 is 4, and 4 times 3 is 12. 4 plus 12 is 16. And now I'm done with that row. And now I'm just going to have to dot this vector with each one of these 4 vectors. So 6 times 1 is 6, plus 2 times 4 is 8, 6 plus 8 is 14. 6 times 2 is 12, and to 12 I'm going to add 2 times 1 is 2. That's also 14. 6 times 3 is 18, and 2 times 6 is 12. 18 plus 12 is 30. And now 6 times 4 is 24, and 2 times 3 is 6. 24 plus 6 is also 30. So A times B is equal to this 3 by 4 matrix. And that, my friends, is how you multiply matrices.